Hello, Archer. So, in this particular lecture, we're going to look at chapter 6 of the type notes corresponding to this series. And chapter 6 is about convergence analysis for line search methods. So, the aim here um, is to prove, obviously, some convergence results. So, to investigate the conditions under which the line search method converges. So, just to set the stage, the generic line search method is given by this iterative procedure. So xk plus 1 is equal to xk plus alpha k times pk, where, as always, alpha k is the step size and pk is the descent direction. So we've been playing hard and loose with the terminology and with indeed our methods. So now it's time to put some rigor on things. So we want to understand the circumstances in which this kind of algorithm converges. So in other words, we want to know when xk tends to x star in the limit as k goes to infinity. And we're going to call this equation 1. So to investigate the circumstances in which the convergence expressed in equation 1 is actually achieved, we need some notation. And for that reason, we introduce the cosine of theta k, and this is the angle between the descent direction and the gradient at iteration level k. And here we're just using some obvious notation that grad f k with the subscript here is the same thing as gradient of f evaluated at the present iteration k. So just to emphasize, in this particular lecture, we don't actually prove the convergence result in equation 1. That will come in a later lecture. Instead, what we do is to prove a key intermediate result, and that will help us to establish equation 1. And the intermediate result goes by the name of Zoutendijk's condition. And it says to consider an iterative line search method, xk plus 1 equals xk plus alpha k pk, where pk is a descent direction, such that grad fk dotted with pk is negative. We're told to suppose that the alpha k's satisfy the strong conditions. And we're also given some conditions on f, namely that it's bounded below in Rn, and that it's continuously differentiable in an open set N containing all of the level sets L. So this is the set of all x such that f of x is less than or equal to fx naught, where x naught is the starting value in the iterative method. We're also told to assume that grad f is Lipschitz in N. So in other words, there exists a Lipschitz constant L such that the L2 norm of the difference between grad f at x and grad f at y is less than or equal to L times the L2 norm of the difference between x and y for all x and y in the neighborhood N. And if all of these conditions hold, then the sum over all k of cos squared theta k times the L2 norm of grad f squared is bounded. And just to emphasize for the idea behind condition 2 in Zoutendijk's theorem, you should have a look at this figure. So we're drawing the level sets where f of x is constant. And these are hypersurfaces in n dimensions, but just shown figuratively here in the case of 2 dimensions. So in particular, we look at the level set where f of x is equal to f of x naught. And then inside, these are the level sets where f of x is less than f of x naught. And this then is our neighborhood. And in this neighborhood, we're required to assume that f is continuously differentiable. So just to emphasize, the proof of Zoutendijk's theorem is in the typed lecture note, but we're not actually going into it here. Instead, we're going to focus on proving a corollary. So the corollary says that if the conditions in Zoutendijk's theorem are satisfied, then cos squared theta k times the L2 norm of grad f tends to 0 as k goes to infinity. And the proof is as follows. So by the assumptions in corollary 6.1, so in other words, the conditions in Zuydendijk's theorem, then we have that this equation bounding the sum, bounding this particular sum, that this equation is finite. So that would be our equation 2. So this is less than infinity. So in other words, this is a convergent series. And so if you have a convergent series, then the general term in the sequence of elements in this series tends to 0 as k goes to infinity. And so cos squared theta k times the L2 norm of grad f squared tends to 0 as k tends to infinity. And so indeed in this corollary 6.1, we should have a square. And furthermore, this corollary now has a very important consequence for us. Namely, if we can somehow keep cosine theta k away from 0 in the tail of the sequence, so in other words, for k sufficiently large, then there exists a delta greater than 0 and a k naught in n, such that the absolute value of cosine theta at iteration k is greater than delta for all k greater than k0. If all of this can be made to happen, then the L2 norm of grad f will go to 0 as k goes to infinity. And in this limit then, we'll have the L2 norm of grad f equals 0, and this is exactly first order optimality. So in other words, if we can keep cosine theta k away from 0, then we get the first order optimality condition in the limit as k goes to infinity. And just an example of how this particular result can be applied, if we look at the steepest descent method, then cosine theta k is actually +1. So we can keep cosine theta k away from 0. We can keep cosine theta k away from 0. So once we can show, or once our f is such that it satisfies the criteria in Zuydendijk's theorem, then the ST method is guaranteed to converge. So we have our first convergence result of the course, named that the steepest descent method converges to a minimum where first order optimality is satisfied once f is sufficiently well behaved as per Zuydendijk's theorem. And furthermore, Zuydendijk's theorem can be applied to quasi-Newton methods, where, as always, the descent direction is given by solving a matrix equation, bk pk equals minus grad fk, and again, provided bk satisfies certain sensible conditions. And this is made clear in the following theorem. So in this theorem, we're told to consider an iterative method where the descent direction is given by equation 3. And then suppose that bk satisfies the following conditions. It's symmetric, positive, definite, and also that this condition on the matrix norms is satisfied. So the L2 matrix norm of bk times the L2 matrix norm of bk inverse should be less than or equal to m, where m is a constant. This has to be true for all k. Then again, we get cosine theta k bounded away from 0 for all k. And this will be an important result that will characterize our Newton type method, such as BFGS. And we will look at the proof of this statement in the next lecture.